They can have both positive and negative voltages, just like when we do our AO channel 0 voltage and our AO channel 1 voltage. You know, we can either have those as series aiding and opposing, and we'll draw in the MIDAC on how we wire this up on MIDAC. All right. So now what would be my what's my next step? Fill in the known. So obviously, you know, now we're going to always kind of be consistent. We're always just going to kind of analyze our circuits whenever possible, going the same way as the electron pass. So we always make sure we maintain that. So we know we have a 1.2 kilo ohm here for R1, 1 kilo ohm for R2, 5.6 kilo ohms for R3. R4 is 2.2 kilo ohms. All right, now what's my next step?
Add them together.
Yeah, so now we can find RT. Okay, so we found our voltage total. Now we're going to find our RT total, and we just have to add them all together. And what do we get for RT then? 10K. Don't forget your units, metric prefixes, 4 digits. So we have 10 kilo ohm total resistance. Then what do I have for, what would be my next step? Find my current. So that's going to be our step 3. How do I find current? Voltage over resistance. So what am I going to end up with?
1 milliamp.
1 milliamp. Okay. Then what's my next step? Yeah. Find the power. Yep. What were you going to say, Brent?
I was going to say put your current throughout the.
Oh, I even like that better. Yeah, we should have done that. Let's even do it. Yeah, because we're getting that. That's a good one, Brent. Yeah, make sure once we determine our current, then make sure we get our current around all of them. So that should be our step 3.
As long as they're in series, right?
As long as they're in series, right. Yeah. There you go. Good. I'm glad you brought that one up, because that's a step we shouldn't skip. We already had that filled in, because when we have a complex circuit, we might forget about what that current was and end up having to recalculate it out again the second time, especially when we get into series parallel circuits. All right. Now we can go ahead. Now we can find step 4, which is our power. And how are we going to calculate our power? Yep, I times E or V. And what do we end up for power total then?
10 milliwatts.
10 milliwatts. Okay, good. All right, now what's the next? Then what's our next step? Yeah. Now here's what we call voltage drops. Okay, so we're going to calculate out what our voltage drops. Remember, voltage drop is equal to I times R, so they're just IR drops. We're just looking at IR drops. And we haven't been using any of these polarities, and we never will be putting on polarities on our voltage drops. All right, so what do we get for some of our voltage drops?
At R1, I have 1.2 volts.
1.2 volts, that's what we got. Okay, 1.2 volts. Okay, R2, 1 volt. Should be seeing a little pattern here. 5.6 volts.
2.2.
And 2.2 volts. And if we wanted to double check our calculations, what can we do to double check our calculations? Add them all up, see if they come up to our 10 volts. Okay? So always make sure you're always double checking your work. All right. Now we have as our last step then is calculating our power. So So what's my power on this one? 1.2 milliwatts. Okay, now power for P2, 1 milliwatt. Where did all my worksheets are this easy? All right, P3, 5.6 milliwatts. And R4, 2.2 milliwatts. If I want to double check that I calculated all my powers up, what can I do? Add them all up and they should equal up to 10 milliwatts. So always be double checking your work. All right, so before we leave this worksheet here, and before we get into, we're going to use this one here for our, before we get into, just double check and see, maybe I did that. I can't remember my worksheet here. Oh, yeah. So what we're going to do in chapter 4, there is your, and this is another page that you should mark, and this is your going to be your voltage divider formula. This is our one of our most common formulas other than Ohm's law and the power formula. This is our next one that we use all the time. We're always building up voltage dividers. Okay? And what you're going to find out, remember I said that typically when we're troubleshooting, we're going to be troubleshooting with a voltmeter. Okay? We're not even so worried about the current and stuff. We can calculate out the current and stuff like that, but we're looking for voltages. A lot of times what we're looking for voltages. And we're not even concerned about the current. So when we're analyzing up a circuit or building a voltage divider or want to know what our voltage is across a certain point, we can use what is known as our voltage divider formula, and that's on page 136, down towards the bottom there. So how I write it is I just go, my VRX, my voltage drop across some component, is equal to Rx divided by RT times my voltage source. Okay, so it's just a ratio. Remember we talked about that. Which one did we? What did we say? Which resistor is always going to drop the most amount of voltage? The highest one. Okay, because of our ratio, the highest one is always going to take the most amount of voltage, and our smallest one is going to take the least amount, the 1K. Okay, and it's based on this voltage divider formula. So if we got a circuit like this and we don't care about the power or current, we just want to know what our test point is, or we want to find out what some voltage drops are, we apply our voltage divider formula. So basically, if we want to find any given one of these voltages, so let's just use R3 because that's the one that's our largest one. Let's just use R3. So what I'm going to do in my calculator, I'm going to put in, so my VR3 is going to be equal to my Rx, which is going to be my 5.6 kilo ohms. I'm going to divide it by my total resistance of that circuit, which is my 10 kilo ohms. And then I'm going to just multiply it by my voltage source. So take 5.6 kilo ohms, divide by 10 kilo ohms, hit your equal sign, and then hit multiply your voltage source and see what you end up getting for a voltage. And you should get 5.6 volts. So make sure you know how to use that, because this will be on our quizzes and on our midterm. What's that? Final. Yeah, on the final. Yep. Did I say midterm?
Yeah.
Oh, sorry. Final, not the midterm, but on the final. Okay? So make sure you have that written down somewhere. This is one that we use. You'll use it through the whole life of this program. Okay? So did you end up with 5.6 volts?
Yep.
Yep, you should. And so we can do that with any given resistor. If we only want to know what the value of this one resistor is, we can just use that voltage divider formula and get our voltage for that. And we're going to use that formula here for our next one. All right, any questions on this worksheet? All right. Let's take a. I don't want to do the whole number thing on that box is covered here yet today. So let's just take a look at. Take a look at some of these. Okay, so here's my polarity. Positive, negative, positive, negative. Okay, series aiding or opposing power supplies. Series aiding. So what's going to be my total source voltage? 75 volts. Okay, and then the rest of it, we know how to do the rest of it. Okay. So that one's that's a series aiding power supply. Series aiding or opposing on series aiding. Series aiding or opposing on this one? Opposing. So what's going to be my total source voltage? 50 volts. It doesn't matter in a series circuit. It doesn't matter where our components are or where our power supplies are. The current is still going to flow the same way. The source voltage is going to still have the potential energy of moving those electrons around. And so this one here is just really demonstrating that it doesn't really matter in a series circuit. I can mix these components all around, and I would still come up with the same numbers and the same current and the same voltage drops and stuff, no matter where these components are, whatever order they are going into that series circuit. So that's one thing to remember, is that when we're analyzing circuits, sometimes it's hard to, when we're looking at a circuit, and we look at it, and we got this power supply here, but then there's another power supply between another couple of components and stuff, and we're looking at it, and we're trying to figure out, is it a series circuit? Is it a parallel circuit? Is it a series parallel circuit? And so we just have to realize that, just because something's not what we normally see in our worksheets, we just kind of have to analyze it. Well, if I draw in the current path, we know the bully on the block is this one here, so we know that my current is going to be going up here, and then we're going to just draw in our current path. And then you're going to analyze the circuit the same way. Just doesn't matter. Okay? So that's what that one's just kind of representing, that just be able to identify a circuit that doesn't look like a normal worksheet. That's kind of your hardest thing, is being able to transfer over from worksheets over into the real world. Everything is nice and spelled out. You have something to follow along with, but when you're doing it on your own, it becomes a little bit more difficult. All right, so that one's series opposing. All right, so here's our here's our next subject then, test points. This is a big one. This is the one that when we look at when we're looking at schematics, and we're trying to troubleshoot something down to the component level or even at a machine level, we use test points for our troubleshooting and to identify if our circuit is good or bad. Okay? So our first step then is that we need to find out what is all our voltage drops, our IR drops. Okay? That's our first thing that we need to know. Again, we always want to draw in our, and then here's where the polarities, the electron current path and the polarities are very important. So we want to do that first. Okay, so is my current going clockwise or counterclockwise? Counterclockwise. And I will let you use your watches on the quizzes and the finals. Then you might want to invest in an analog one. Okay. So there's our current path. There's our polarities, which then we're just gonna fill in all our knowns. So we know that we have a voltage total of 24 volts. R3 is 1 kilo ohm, so we're just filling in all our knowns. R2 is at 1 kilo ohm also. Looks like it. And R1 is 1 kilo ohm. All right. So there's all our there's everything that we know. What's our resistance total going to be?
3 kilo.
3 kilo ohms. Okay. So we said that everything, all our voltages are going to drop proportionally across our components. If every one of them is a 1 kilo ohm, which one's going to drop the most amount of voltage?
Equal.
They're all going to be equal, right? So we got 3 different components. They're all equal to 1 kilo ohm. So how much voltage is going to be dropped across each one of these components? 8. Okay. So sometimes we don't need to know formulas. Sometimes we get so carried away of using our formulas all the time that we also put them in our calculator and we get the answer and go, oh crap, I should have seen that. So sometimes we only need to use our calculators. Just the logical thinking of how that all goes. All right. These are all considered our voltage drops. All these 8 volts are our voltage drops. No polarities. Okay? Now we're going to find out what our test point voltages would be. Find out what your test point voltages are. We can have it, we'll use VAG here. We can have it as, you might see it as VAG. Typically they're subscripts there on the whenever it's possible. I can't do subscripts in this program here. So you just got to make the assumption that it's measuring my voltage at test points A and G. I can also have it as, you might see it as TP AG. Okay? Sometimes they call them as a test point. Test points, point A to G. Both test point A to G. Doesn't matter if they're using V or TP. All they're just doing is identifying when we use V, we're identifying that it's a voltage. Then when we're looking at our test point voltages, what we got 2 letters here. One's going to represent what our polarity is. This is going to be always our red lead of our meter. The second letter always represents the point of reference. Doesn't have to be our ground. It doesn't have to be, it's whatever our test point identifies as our point of reference. It doesn't have to be our, it doesn't have to be our ground symbol here. It doesn't have to always mean that. And this is where our black lead is always going to go. Okay? If I have, sometimes what we have is, because we do identify where our reference point is on our schematics, we have the ground symbol, that's our point of reference. A lot of times we don't even have to identify the second letter. So VAG would be the same as VA. Okay? Because here's G, here's test point G, that is my point of reference. So I wouldn't even need to put in my second letter. I could just do VA. And this one here, that first letter is still going to be representing my polarity, my red lead again. The black lead is going to be going on to the point of reference, the ground. So if this one's blank, then this one's just going to go to your ground or your point of reference. Okay? Both one and the same on this particular one. Okay? I can identify it either way and I'd still get the same test point voltage. All right. So here's where our polarity and all that is going to be the big role in it here. So what you want to do is you're going to look at it and you're going to say, okay, I got test point A to G. You're going to put your red lead on A, put your black lead on G. Once I identify where that black lead is, this one never changes. This never moves. We always bring our red lead down to our black lead, calculate out what our test point voltage is. Okay? So what I'm going to do is I'm just going to bring my red lead, which represents my positive, and I'm going to just bring it around, and I'm always just going to, everything we do, we just add everything together. We're just going to take the sum of something. So I'm going to come around, and when I come around and follow doesn't matter if I'm following my current path or not, we're going to go around this way here because it's the most logical one. And come up and I'm going to look at my first sign that I come to. And I got a positive. I got a positive on a positive. So I'm going to have a positive number. So I'm going to have a positive 8 volts plus my first sign I see, another positive. So I got positive on a positive. So it's going to be another positive number. So I'm going to have positive 8 volts plus another positive 8 volts. Gives me what for a total?
16 volts.
16 volts. And what did I say always about test points? What do they mean?
Polarity.
Polarity. So we know that my polarity across this one is positive 16 volts. Okay? So make sure you get your polarity in there, 4 digits, and your units. Okay? It doesn't matter which way you go, just as long as you follow your current path. So, again, test point A, my red lead's going to go on test point A, black lead's going to go on G, black lead never moves. I can go the other way. I can come around this way. I got a positive. My red lead comes down to a positive, so I'm going to have a positive 24 volts. Plus, now I got a positive on a negative, so I'm going to add a negative 8 volts. So what's a positive 24 volts plus a negative 8 volts? Positive 16 volts. Doesn't matter which way I go, I'm always going to get the same reading. I'm always going to get the same number. I could even go, if I really wanted to, I could go from here, I could go around 5 times, come back, end up my red lead on my black lead, and by the time I add and subtract everything, I'm going to end up with 16 volts. Okay? All I have to do is just make sure I follow a path, and it'll always come up, so it doesn't matter how complex my circuit is, I just follow the path, bring my red lead down to my black lead, and I'm going to measure, and I'm going to be able to identify what that test point voltage should be. Okay? So if we're drawing up schematics, we're building up a prototype board or building up some schematics, and we're giving them some troubleshooting test points on our schematics, that's what I'm going to do when I'm going ahead and setting up those test point voltages, so I can tell somebody a good test point voltage should be 16 volts. If they come over and the next person comes in, they're running into problems, and they identify that I don't have 16 volts at this point, then they know that there's something probably wrong, or that I don't have 8 volts at that other point. You know, they're going to know that there's something wrong with that circuit. Then that's when our troubleshooting kicks in. But we have to have. But if I just come in and I just say, yep, I got positive 16 volts there, you know, and I check all my test points, everything matches up, then I know that circuit's working. It's probably something else then. All right. So then let's take a look at the second one. So DBG. So where does my red lead go?
B.
On B. Black lead goes where?
G.
G, right here. Okay, so what I have to do is just bring my red lead down to my black lead. First sign I see is positive, so I got positive on a positive. So I got positive 8 volts. So I'd have a positive 8 volts. Okay? My next one, my C to G. What do I have? Where do I put my red lead?
C.
C. Black lead goes on G. Bring it around, so I'll come in, bring my red lead over to my black lead always. Black one never moves. I got a positive on a negative, so that's going to make this a negative 8 volts, right? I'm going to have a negative 8 volts. My red lead's back to my black lead, so my end result is going to be a negative 8 volts.
Question on positive numbers, do you want a positive in front of the number, or can it be blank?
Nope, always has to have polarities. Because if we do, so just because we always know that there's going to be polarities, if we don't have one in there, did you forget to put the minus sign? Or did you really want that to be a positive?
I mean, does that go then for all numbers then? I guess what I'm getting at.
For all numbers where? Well,
Even if in the circuit doesn't have a negative voltage, are you going to want that as a, like the 4-digit rule, do you want to have a positive all the time?
always, no, this one here wasn't a positive. This one here is a negative.
No. Any number that's going to be positive,
Yep.
are we going to
Always put a polarity on it.
always put it in there?
Yep,
So
and
like-
that's our rule. Remember that was the rule that we looked at earlier here on our
Okay, so I just want to.
lab rules? Always put, test points always require
Okay, so
polarity.
test points, okay, not like voltage.
Nope, because,
That's-
here, well, let's just, that's just a good question, because we didn't know what we were looking at, so let's just bring up our little rules here.
I get the part about the test point, I just wasn't sure if it.
Yep,
all
I know what you're getting at.
Yeah.
Yeah, so here's on our worksheets and lab rules, you know, if we come down here, here's where I think you're trying to get at. Like voltage drops. You know, voltage drops, we never require polarity, because they're just voltage drops. We don't know which way we're measuring from. But all test points then always require polarities. Yep. Yeah, always require polarities. You know, let's even use one as a good example here. And you know, how simple that rule seems, it's amazing how many people will not follow that rule. And they'll get the whole worksheet wrong if they don't put their polarities in there. So for example, what would I get for test point VGG?
0 volts.
Okay. Yeah, there you go.
Yeah.
Yeah. Don't forget, even my 0 volts, because the rule is, again, because of the consistency of it, that the rule is all test points require polarities. So even our 0 volts will get that, and we'll get plus or minus 0 volts so that we always maintain our rule. If we go relaxed on one, then we get relaxed on the positives. We're always good about the negatives, but then we get relaxed about the positives. But when we're documenting things, we want to make sure that we totally identify that, yes, this is definitely what I wanted. I wanted it to be a positive 16 volts. There was no question about it. Nope, I didn't forget to put the minus sign in there. I didn't forget to put the positive sign in there. That's what I wanted. That's why we always say that and keep that rule. Even on our plus or minus 0, just to keep it consistent. All right. So we got some nice easy numbers here. So what would I get for test point VCB? What would I get for a voltage? Where's my red lead go? C. Black lead goes where?
V.
B. Which way do I want to go? This way or this way? Doesn't matter which way I go. So we can go either way. So let's just go with the current flow. Yep, so we get a negative 8 plus another
-8.
negative 8. I'm going to get what?
-16.
Negative 16 volts. Okay? And that's important because, you know, a little on these test points, these are what we really consider outputs. Okay? So if I had an op amp or something like that, and I needed this negative 16 volts going into my op amp, I know I could take it from C to D, and I'd get my negative 16 volts. Okay? Even though I don't have my reference, not using my reference, I'm going to get a negative 16 volts from C to B. Okay?
So
So
if you were to go the other way, then you would include the voltage source, because if
Yep,
you just
so if I went the other way,
it'd be -24 volts.
yep, negative 24 volts plus
8 volts. negative 16
Gives
volts.
me negative 16 volts. Doesn't matter which way I want. So if we'd, let's make it so we can see this a little bit easier. So once we identify the individual test points, we got plus 16, we have plus 8 volts. G is going to be plus or minus 0 volts, and C is a negative 8 volts, okay? Remember, it's respect to ground, okay? This is at test point C, it's respect to ground. My black lead's on my point of reference. That's where all these voltages came from. It's respect to ground, okay? So if I said, what's my voltage at test point C to B, just like we did? Another way of doing it would be that I know that test point C is a negative 8 volts. I know test point B is at positive 8 volts. What's my potential difference between those 2 points?
Plus or minus 0?
Okay, so look at it, treating it as a number line now.
Negative 16.
So B is C, so it should be C to B. So it'd be like plus 16 volts. Okay? Or not plus 16 volts. Okay, because my red lead is on a what? More negative number, right? My black lead's on a more positive number, so it's going to be inverted. So the potential difference between test point C to B is going to be what?
Negative 16,
Negative 16
volts.
16 volts, okay? You don't always have to bring your red lead to your black lead. If you identify what each of your individual test points are, then you can just take the potential difference between those 2 points. So it'd be like me hooking up a voltmeter up to this thing. If I took a voltmeter and I went, okay, here's my red lead, here's my black lead. Okay, if I put a voltmeter across there, I'm going to measure that potential difference between those 2 points. That is considered just like a source voltage. It could be treating it as my AO0 voltage respect to my AO1 voltage. Okay, I'm just measuring that potential difference between here, and I would then I would get a negative 16 volts going across there.
We were talking about this in the group, and I wanted to show them that they can measure a negative voltage with an analog meter. So with using that one, you'd have to reverse the leads in order to do it. You'd have to knowingly know it.
That is correct. When you're doing an analog, when you're using an analog meter, I would have had to know that this one's going to be more positive, this one's going to be more negative, and then I would have to know in my head that I flip the leads around.
And so you have to reverse the leads. So
You'd have to reverse the leads, yep.
So instead of going by the rule here, you know the rule, but switch it so that you know that you're reading a positive,
Right.
negative voltage.
Yes. Yep. Exactly. That's a good point.
So BC should be positive 16.
And BC would be a positive 16 because then my red lead on BC then my red lead goes where? B. My black lead's going to go where? C. My red lead is on a more positive number than C, so we know it's not going to be inverted, and so then I would get a positive 16 volts. Okay? And I can use those as outputs. That would be like me setting up, it's almost identical to me setting this up as this would be AO0, channel 0, and set it up for a negative 8. And this would be my analog output, channel 1, set up for a positive 8 volts. Okay? If I measure across AO0 and AO1 with those voltages set up that way, I'd measure my 16 volts, depending on which way my polarity is. Okay?
Take a break.
Oh, yeah, we better take a break. Holy crap. The previous one, we had our components in a kind of in a square box and stuff. We had components scattered out all over the place. When we're actually analyzing circuits, and we're really going to get, we're going to do it quite a bit when we get into series parallel circuits, into our larger circuits and stuff like that. But what we call this is sometimes when we're analyzing circuits or when we're drawing them up, what we like to do is we'd like to draw them as a straight line. And when we say straight line your circuit, typically what we always do is we put our power supply on the left-hand side, and then all our components on the right-hand side. Okay, so we just redraw up our schematics as we're trying to analyze them. We redraw them up, so all our components are on the right-hand side, and they're all vertical. Okay? And it makes it a lot easier to troubleshoot than to have components scattered out all over the place. You know, because now here I can just identify, here's my test points, just going right down. I have the same number of components, but it's a lot easier to analyze it going this way. It's a lot easier to see what's happening. And so we call that straight line. And when we get into chapter 6, then we're going to be straight lining all our circuits. We're going to go ahead and put the power, we're going to redraw them up, put the power supply on the left-hand side, all our components on the right-hand side, and draw them all vertical. Then when we're analyzing them, we're just going straight down, boom, or up, depending on referencing it to ground there. So just kind of keep that in mind there. That straight line makes it a little bit easier to see how that goes. And so towards the end there, on the other worksheets there, I started doing them as more of a straight line. Now in your lab there, for lab 7, I think it was, lab 7, okay, so we're looking at all these test points, and these are just outputs, okay? So for example, here's my ground, here's my reference point. This is going to be my plus and minus 0 volts, okay? I have my power supply here, but all these are going to be, and my polarity across my power supply, or all my components are going to be like this. So we can treat these things as outputs. And I'm just going to throw some random numbers in there so we can save some time here. But for example, I know that without even doing any numbers, I know that all these test points referencing it to ground are all going to be positive. So test point A is going to be a positive voltage, test point B is going to be a positive voltage, test point C is going to be a positive voltage, but then test point D is going to be a negative voltage. Okay, so this one's going to be, so test point D is going to be a negative voltage. I'm just going to throw some arbitrary numbers in here so we can see how this would work. So I'm going to just say, test point A is going to be plus 5 volts, test point B is going to be plus 5 volts, and plus or minus 5 volts. Okay. You don't have to, just kind of going to explain to what you're going to be doing in your lab on your further investigation. But anyways, these are all outputs. So for example, if I needed an output going into another circuit or another device, and if I needed 10 volts, then I know. These are all screwed up here. Hold on, I got it. That's not what I wanted. I wanted these as voltage drops. No polarities on my voltage drops, so just 5 volts, 5 volts, 5 volts. So then I know that test point A, referencing it to ground, I'm going to get plus 15 volts. I'm going to get plus 10 volts at test point B, referencing it to ground, plus 5 volts, referencing it from C, and then here I would get a negative 5 volts. Okay. So if I needed, and so these are little or they test points, they might be outputs going to another circuit or something. So for example, if I needed a 5 volt source, I could come off with my leads, come off with test points C and G, and go into my circuit, and I'd get a plus 5 volts. If I needed something at 10 volts, I could go from B to G. If I needed a negative 5 volts, I can go from D to G. Okay? So these are just outputs that are going into another circuit. They're also test points. If I needed a plus and minus 5 volts, or a total, of 10 volts, I could come off of D to C, going into my circuit and then referencing it to ground, I would get a plus 5 volts and a negative 5 volts going into my circuit. Well, since these things are, this is just kind of what we call, this is what we call an unloaded voltage divider. I'll just put VD, unloaded VD there, voltage divider, meaning it doesn't have any load across there. So if I'm going to actually use, if I'm going to actually start using some of these outputs, what happens is that when I start putting in, components in here, or putting in a load across here, it's going to load it down. So for example, if I came off of my, so I got plus 5 volts here, and this is my plus and minus 0 volts. If I come off of here, and I put a load across there, and we can treat any load, we use it as a symbol as a resistor, and come across there, and I put a load across there, it's going to load that down. I have what I call, this is what we actually end up calling the series parallel circuit. This is chapter 6. This is where we really talk about the loaded voltage dividers. But they're introducing it to you just so you can kind of get a somewhat of an idea of what's going on. They're having you load down this voltage divider. What happens is that, again, all my current is going to be coming out of my power supply. This is all part of my series circuit, so all my current's coming through there. I got all my current going through R4, but it's going to end up going into a current node here. Okay, I'm going to give it 2 paths for that current to go. Okay, so I got my total current going in here, and then my current is going to split. A portion of it's going to go this way, and a portion of it's going to go this way, depending on what the resistors are. And then those 2 currents are going to combine again back up into the current node here, and then go back in, and all my current's going to go through R2 again, and R3, and then back into my power supply. So what happens is that when I start to add in more resistance across another resistor, what happens is that my circuit becomes more conductive, okay? If I add in a series circuit, because my formula RT is equal to R1 plus R2, as I keep on adding more resistors into a series circuit, my resistance is going to start to go up. In a parallel circuit, it's just the opposite. As I start adding more resistors in parallel across my load, my RT is going to actually end up going down. As my resistance starts to go down, my current starts to go up. Also, as my RT goes down, what's going to happen to my voltage going across that? So if my RT starts going down, the voltage going across RT, assuming that's a series parallel circuit, my voltage is also going to go down because of V is equal to IR. If R starts to go down, so does my voltage. So as I start adding in more resistors across another one of these components across this voltage divider, another name for a series circuit, the voltage divider, as I start adding in more resistors across one of these components, the total resistance of these 2 combined are going to start to go down. The R is going to start to go down, and then if R starts to go down, so does my voltage drop. So my voltage drop across R3 is going to go down. And all they want you to do is to start put in a load across that circuit in the further investigation. They're just going to have you put in some kind of a resistor, and you're going to load it down until this drops down by about 10%, I think is what it is. So when you see that voltage drop across R3, for example, and drops down to 4.5 volts, you know that you went down about 5% or 10%. And so that's all they're really looking for you to do is just put that resistor across the other resistor in our voltage divider, unloaded voltage divider, and we're just going to measure that voltage across there, and we're going to watch that voltage start to drop as we put in some other resistors. Another alternative, and I really want you guys to start getting in the hang of doing this, is that if I just put in more resistors and stuff, or put in different values of resistors, instead of plugging in and pulling in and out different resistors, we can always use our potentiometer as a rheostat. Make it a variable one. So then you can go ahead and put in a variable pot in there, start tweaking it down so you start dropping the resistance of that potentiometer down, and watch that voltage until it drops down to that 10% value. Once you drop it down to that 10% value, turn your power off, remove your potentiometer from the circuit, and measure what that resistance was. And that'll tell you what your resistance was. That will tell you how much you loaded that circuit down. Okay? So they're kind of getting you going already for chapter 6 in that further investigation. I think it was in lab 7. Maybe lab 8. Let's see here. Lab 8. Lab 8, they're going to have you start doing that. Okay? So that's all they're looking for in that further investigation. I think otherwise everything else is pretty straightforward. I just got done talking to Bob. He's going to make himself, he's always available after noon, and he can help you out with the labs and stuff like that. He's tied up today, so he's not going to be around today. But if you need help with your labs, have Bob help you out, hooking up your labs, and having him explain to you what you need to do on these labs. And I can too, if I'm around, but you remember, I'm going to be, gets pretty chaotic. You can see how chaotic it gets in the lab room because I'm running around trying to get labs checked off and stuff for people and stuff like that. So it's good to use your other resources if you can. I'll try helping you, but remember, ask your one lab partner for help, and then ask somebody else. And if you all three can't figure it out, then come over and get me, and we'll take a look at it together. All right, so go ahead and practice up on those on these worksheets. We only have 5 minutes. I think people are starting to understand how to use that potentiometer. Just refer back to Lab 6 if you can't remember how to use that potentiometer, or we can kind of go over it. I think we'll just kind of hold off. We'll hold off on these last part of these worksheets where the potentiometers are. These potentiometers are big ones, and we can have them all different configurations. This one's wired up as a potentiometer. I'm showing you, the voltmeter, how you'd hook up your voltmeter up to it. We have different configurations, and so I want to spend a little bit of time on that. So I think when we go over the midterm on next week, we'll probably do this like on Tuesday or Wednesday when we go over the midterms. Then we'll go over the potentiometers. There isn't too many of the potentiometers in the lab other than Lab 8 there. You have to use a potentiometer, but it's the same way that we used it in Lab 6. Okay? Because this is pretty lengthy. Okay? So practice doing your test points. If you have questions on your worksheets, I always will help you out on your worksheets. Any lecture type stuff, I'll always help you out with the lectures, and then also Bob. So. I know Sean brought up one here to be a good one here to kind of go over. When we're working with those potentiometers, so here's our blue potentiometer, and it's got 3 leads coming out of there. Okay, what we have in there, we have a fixed resistor that's going across pins 1 and 2, and then we have our wiper that's going across there. Okay, now they've been jumpering these two leads. Okay, so we've been doing that in our proto board. Okay, so when you're measuring your resistance, when you're coming off with your ohm meter, you're coming out from one pin, and it doesn't matter now because since we have our middle wiper tied to our outer wiper, we can either tie it to our middle wiper or this one. We got that piece of wire that's jumping in there, and so then that can come down to the other one. Okay. So what you have is, and that'll give you your measure of resistance as you turn your thing. That's gonna, as I move it more, if I move my wiper more this way, I'm going to get more resistance. If I move it this way, I'm basically bringing this piece of wire over to this side, and it's kind of shorting out that whole resistor. I'm not going to get as much resistance in there. So you have that jumper in that breadboard. And then they have you go and they have you pull it out. Remember I said you got to pull it out, or you have to disconnect it from the power supply, disconnect it from the circuit and stuff. You know, it might be easier to leave the potentiometer in the breadboard and then just remove the leads that are going to it. So you just only have the potentiometer with that lead. Because what's going to happen is that even though you adjust it, so let's just say this is a 1 kilo ohm potentiometer, you have it in mid-range, okay? With that jumper in there, the 1 kilo ohm rated potentiometer, but with that jumper in there, and we set it for mid-range, across, we'll just number this 1, 2, 3, across pins 1 and 3, or 1 and 2, I'm going to get 500 ohms. Okay? So across pins 1 and 3, I'm going to get 500 ohms. Then if I did the same thing here and I pull it out of my circuit and I leave my jumper in my circuit, I don't have this jumper in here. What's going to happen is that I'm not going to be shorting out this half of that resistance. So now I measure across pins 1 and 3. Now I'm going to measure my 1 kilo ohm. Okay? So the easiest way is if I leave that potentiometer in there, remove any of the power or anything that's going to that thing, bring in your ohm meter on your breadboard and measure it. So you get either your 500 ohms, so you're not measuring this 1 kilo ohm when it comes out. And then another one was that it was getting flipped around. Even if you went to, so if I got it set at mid-range here, across pins 1 and 2, I'm still going to get 500 ohms, but from pins 1 and 3, I'm going to get 1 kilo ohm. Okay? So here I would be correct, but here I would be incorrect. But if I set this thing up for, a lot of times we're not exactly at mid-range anyways, we're at some other portion of it. So we'll just say now we're set up so that across pins 1 and 2, I have 250 ohms. That means I'm going to get 750 ohms across pins 2 and 3. Okay? So when I had that jumper in there, if I jumper off pins 2 and 3, I'm basically shorting out this 750 ohms. So when I go and measure across pins 1 and 3 with the jumper in there, I'm going to only measure 250 ohms. I pull it out of my breadboard and I leave the jumper in there and I go across pins 1 and 3, I'm going to measure 1K. And if I go across pins 1 and 2, then I should measure the correct things. So when you're looking at that, kind of think about what's going on inside that potentiometer so you can understand, am I at 750 ohms or am I at 250 ohms? Or should I be at mid-range? Think about how that thing is being wired up and how this piece of wire is that's actually just shorting out. As I move that wiper over this way, I'm just shorting out some of that resistance. If I pull it out of my circuit, then I'm removing that short from that resistor, and then I'm measuring my full resistance again. So just kind of pay attention to that when you're doing those labs, and I think you should be okay on that. And then we'll go into further details on this. This one here we're kind of using it as a rheostat to give us a variable resistor. We're going to be looking at it as more being as a potentiometer, looking out for some different voltages and stuff like that. And that's how we use them for controls and stuff. So we're going to really kind of be focusing on how we're using them as potentiometers, not so much as rheostats like we've been seeing in the circuits. We use them both ways all the time, but potentiometers we use a lot for speed controls and different kind of controls. So, all right, that's good enough for DC theory. I'll let you take a